Hello, I am Manoj Deshpande, a digital media PhD student at Georgia Tech. I will be presenting Observable Creative Sense-Making, a method for quantifying improvisational co-creative interaction, written by myself, Dr. Milka Trajkova, Professor Andrea Knowlton, and Dr. Brian Magerko. We'll begin by giving context and motivation to this work. Co-creativity or collaborative creativity and improvisation with others are essential day-to-day human practices. They are crucial in helping us make sense of our complex and dynamic environment. However, as standard as these practices are in our lives, it rarely characterizes our interaction with a computer. Furthermore, we have little understanding of how computers can co-creatively improvise with us in embodied domains. Let's look at an embodied activity like dance. Here we see two professionally trained dancers at Kennesaw State University indulging in an open-ended movement improvisation exercise. While these dancers effortlessly improvise, they have layers of knowledge, information, and stimuli that impact their creative choice making. Now, can we facilitate such an embodied and rich interaction with the computer, specifically an improvisational AI agent? Yes, we can, but to do so, we must first develop reliable methods to interpret and quantify the interaction dynamics in such collaborative embodied improvisation. Hence, we propose a new method to address this gap called Observable Creative Sense-Making. OCSM builds on previous work by Davis et al. On creative sense-making. Therefore, let's briefly review CSM and related theories. Davis et al. Designed CSM as a video analysis tool to quantify and evaluate open-ended creative collaboration. CSM is based on participatory sense-making and free energy principle. PSM is a cognitive framework proposed by Dieger and D. Palau. It refers to building an understanding of our environment through collaboration and often involves physical exploration that informs our decision-making processes. The free energy principle claims that cognitive agents continually strive to reduce environmental surprises by modulating free energy to go from an unclamped mental state to a clamped mental state to be at equilibrium. According to CSM, individuals alternate between perceptually unclamped, clamped cognition and physically unclamped cognition state. We can use the CSM tool to continuously code the behavioral markers to the corresponding cognitive states. As a result of this, we obtain the sense-making curve. We can uncover the interaction patterns by studying the individual sense-making curve, comparing it and aggregating it with their partner sense-making curve, resulting in creative trajectory of the interaction. We decided to apply CSM to study dance improvisation. Here, we will discuss the results from it. We conducted 3 improvisational movement sessions with 2 dancers from KSU in each session lasting for 5 minutes and then retrospectively self-coding the CSM states. We hope to identify behavioral markers for when dancers switch between clamped versus unclamped CSM states to develop the codebook. Graphs here show the self-coded sense-making curves of 6 dancers across the movement sessions. As we can see, there's a lot of variation in the data coded by the dancers. Dancers also expressed that the cognitive states and the terminologies like clamping and unclamping were unclear and confusing. Since these internal mental states are not observable, we could not ensure data correctness, nor were we sure of replicability of the data. Overall, the sense-making curves and the subsequent analysis were ineffective in informing us about the interaction dynamics. We also were not able to identify behavioral markers to develop the codebook. Even though CSM has been successfully applied to study activities like written play and collaborative drawing, we cannot effectively use CSM to explore more embodied activity like movement improvisation. This motivated us to reformalize CSM for better studying embodied improvisation. Let's look at the theories we considered for reformalizing CSM. According to DiPaolo and Dieger, sense-making is not a single state and varies corresponding to the degrees of participation by the interactors. Accordingly, individual sense-making corresponds to the state where both individuals are mostly self-exploring. Orientational sense-making is when one individual tries to influence or get influenced by another sense-making activity. In joint sense-making process, participation is the highest among the individual and shared meaning emerges. Sense-making and emergent meaning construction are processes that are closely related to creativity, and novelty and appropriateness are common themes across creativity definitions, as Anna Abraham highlighted in this diagram. From these theories, we identified 3 central elements when dealing with open-ended, embodied, collaborative improvisation. the level of participation of each individual corresponding to emergent sense-making, the level of newness of idea generated or explored within the improvisation, and the level of appropriateness associated with each action within the improvisation. Therefore, observable creative sense-making has three dimensions of measurement: participation, newness, and appropriateness. Each parameter has four observable states for video coding. I will briefly talk about the 4-point scale for each parameter. For more details, please refer to our paper. For participation, state 0 is no participation, state 1 is individual sense-making or self-exploration, state 2 is responding or reacting to partner's movement, and state 3 is joint sense-making. This state marks the highest participation by the individual. The states for newness and appropriateness are based on Cooper et al.'s micro-creativity framework. For newness, state 0 is repetition, state 1 is making minor modifications to previous movement, state 2 is making major modifications to an earlier movement, and state 3 is new movement. For appropriateness, state 0 is off-task movement, state 1 corresponds to movements that are somewhat related to the given task, state 2 categorizes movements related to the given task but is not exactly what the prompt asks. Lastly, state 3 marks the movements that are explicitly what the task asks for the individual. Like CSM, OCSM is also a web-based tool with an embedded video player, and graphs correspond to each of the parameters. The coders will have to use the slider on the right side of the graph to apply the qualitative code to the video. OCSM differs from CSM in three key ways. In CSM, coding states are for internal hidden cognitive levels attributed to behavior markers. In OCSM, the coding states for all parameters are for observable behavior markers. In CSM, the creative trajectory derived from cumulative integrals of individual sense-making curves captures the interaction dynamics. In OCSM, the interaction dynamics are captured through participation, newness, and appropriateness curves. CSM uses the free energy principle to imply creativity implicitly. OCSM captures creativity explicitly along the dimensions of newness and appropriateness. To validate OCSM, in other words, verify if the parameters in the corresponding cognitive states are observable. We designed a video recall study in a dance improvisation class taught by Professor Andrea Knowlton at ASU. We had 16 dancers in the class who participated in the study. All dancers were trained during the course of the class on embodying and improvising using Laban action efforts. A clear indicator to validate observability of OCSM parameters is if the OCSM curves coded by dancers are similar to the OCSM curves coded by people just observing the dance. But observation can be in real time, that is, seeing the dancers live, or recording of a previous dance session. Therefore, we divided 16 dancers into 3 groups. 6 participants, the dancers who will do the movement improvisation, 6 observers, the dancers who will observe the movement improvisation live, and 4 blind observers, the dancers who will watch the recording of the movement improvisation. The participants indulged in a 2-minute movement improvisation exercise based on a given prompt and then self-coded the video recording retrospectively after the improvisational exercise. Simultaneously, the dancers who were observing the participants also coded the session, and the dancers who were blind observers saw the recording and coded the session. Here, we can see OCSM curves for a single participant P2 from dance improvisation session between P1 and P2. The participants coded the curve shown in blue at the top. The assigned observers coded the curves in red in the middle row. Lastly, the blind observers coded the curves shown in black in the bottom row. Each graph within a row corresponds to one of the parameters in the OCSM. The x-axis denotes the time elapsed during the interaction, and y-axis corresponds to the observable states. To understand the overall effectiveness of this method, we took an average of all participant-coded curves and compared it with the average curves coded by observers and blind observers for all the dancers, as we can see in the graph. Now, if we overlay these curves on each other, we can visually see the average participant-coded curve is very similar to the curves coded by observers and blind observers for all 3 parameters, thus verifying the parameters are indeed largely observable. We also noted that all parameters have a strong positive correlation with an R value of greater than 0.7. As we can see, these graphs that compare the 3 parameters of average OCSM curves as coded by the participants. The green line represents a simple linear regression line that indicates a positive correlation among the parameters. The high correlation provides empirical evidence that these parameters work well. For more details on this work, please refer to our paper. Thank you for listening.